to the video on Introduction to Linear Regression. Regression attempts to model the relationship between a set of dependent variables represented by y and a set of independent variables represented by x. Okay? So linear regression is a type of regression analysis which assumes the set relationship to be linear in nature. Therefore, the aim to model a set of variables using another set of independent variables using a hypothesis function which is assumed to be linear. Now we first take a simple case of linear regression, assuming both the features and the labels to be having only one dimension. Now such case is commonly known as simple linear regression. Okay? Now since we assume a linear relationship, we estimate the random variable y, you can see here, okay, using the hypothesis function which is denoted by f that you can see here, with the domain and the codomain sets as R, which is the real set, and this hypothesis function is given as shown by theta 0 plus theta 1 times x. Okay. Now our task in regression, which is in this case, would be to estimate the proper values of parameters, the theta 0 and the theta 1. Okay. Now consider an example with the data as given in this table, right? So you can see that these points are being plotted here. So this 1.5, 1.0 is this point. This 2.0, 2.0 is this point. This 3.0, 2.5 is this point, and so on. I mean, all these points are actually plotted on this graph, right? So this red dotted line, it shows the estimate of the hypothesis function, and henceforth the proper estimates of the parameters, the theta 0 and the theta 1. Okay. However, we need to define which set of parameters do we indeed call as proper. So you can see that all these points are actually plotted on this graph, right? And this line is the best fit line. So basically this line is the one that will estimate the predicted values of these points. I mean the points of this data set, right? Very accurately. I mean more accurately than any other line that is possible. Okay. So this line is basically a linear function. Okay. So this can be represented as theta 0 plus theta 1 times x. Okay. So x we get from here, right? So basically we have to find such a best fit line, and hence we have to find the theta 0 and the theta 1 that are for the best fit line. Okay. Now this is decided by optimizing what is known as the cost function. Okay. So basically, like as pointed out earlier, we need to find the values of theta 0 and theta 1 for the case of simple linear regression. Okay. Right. So in order to do so, we assign some cost for each value pair of theta 0 and theta 1, and then we work to minimize the set cost. Okay. So although it is up to us to design the cost function, which could be as simple as theta 0 plus theta 1, but however, we must ensure that the cost function must be concerned with the estimate of our hypothesis function. Okay. So therefore, the cost function needs to be designed keeping the original task in hand, which in our case is simple linear regression. Okay. Now suppose we have a cost function. Okay. So this j theta 0 comma theta 1 is the cost function, and this when minimized would give us the proper values of the parameters in the task, which is theta 0 and theta 1. Then we can formulate our objective as to minimize this cost function for the values of the parameters iterated over the domains, which we assume to be equal to the real set. Okay. This objective is represented as an optimization problem as given in this equation. Okay, so essentially this is the cost function, and we have to find the theta 0 and theta 1. So these theta 0 and theta 1 will be the ones that will be obtained in the case when this cost function will be the minimum. Okay, so although we can design multiple cost functions, the most common one for linear regression is the least squares cost function. Okay, the least squares cost function is as given in this equation, this one that you can see here. So you have to notice that it is simply the sum of the squares of the error we incur for each data point. Okay, so that is, we sum over the squares of the difference in the real value of the variable y and the estimate that we obtain using the hypothesis function for this data point, right? So you can see that this is the real value for this parameter y, and this is the estimated value for this parameter y. Okay, and yeah, the intuition behind the given cost function is that we wish to minimize the difference in the estimate we provide using our hypothesis function, and this difference must be absolute. Okay, so it is also possible to use the absolute values for the errors instead of the squares. However, as will be shown later, taking squares provide us with good results and with extreme ease. Okay. Now, using the same concepts presented for simple linear regression, we can extend our modeling to linear regression where only the labels are one-dimensional. Okay, so that is, we can have multi-dimensional features. The hypothesis function in this case can be written as shown in this equation, this one. So basically you can see that the labels, they will be one-dimensional, but these features, these denoted by x, so it is multi-dimensional. So this x can be broken down into x1, this x2, x3, and so these are various dimensions for this feature x. Okay, so we use this hypothesis function in that case, and we also use the least squares cost function with the same objective in this case. Okay.